Welcome to another lecture in this series. Today we're going to learn about operational amplifiers, in short, op-amps. So far we have learned about individual electrical components such as capacitors, inductors, and resistors. Op-amps are an example of what we call integrated circuit or IC. For the integrated circuit, we take individual electrical components together and we manufacture them on a wafer, on a single wafer, to produce a component that will give us some functionality, whatever we designed it for. In the case of operational amplifiers, they are used to amplify the input. So the symbol for the operational amplifier is this. We have a triangle which can take two inputs. So we have two input terminals. One of them is called non-inverting, referred to as plus. So this is non-inverting. And then we have another input terminal referred to as minus, and this is called inverting. And here we can feed input. So this could be an input voltage V in 1, V in 2. And then because these operational amplifiers are used to amplify, have to have a power supply to power the op-amp. So we have, this is V supply, so let's call it V plus, V minus. And then we have an output that we take from this terminal. So mathematically speaking, this is the symbol of operational amplifier, and as we have mentioned before, inside this you have a lot of simple individual electrical components that make up this chip. We can use this op-amp in two different configurations. The first one is called open loop gain. So we just have V out, and then we have some sort of gain. Let's just call it AOL, OL as open loop, and then this is going to amplify the input. So here we're supplying two inputs for two terminals, so we're just going to take the subtraction of the two. So V in 1 minus V in 2 as an example. And then the second configuration that we can use this op-amp is in the closed loop gain fashion. So for that, we're going to have a feedback loop going from the output to one of the input. So let's just say connecting it to V in 1. So this is called closed loop gain. Here, same thing. So we have V out, and then this is going to be referred to as ACL, closed loop, and then same thing, V in 1 minus V in 2. The difference between the two is, so this open loop gain is very large, like it's almost 10,000 times, which is not what we want usually. To construct a op-amp, to use that in the open loop configuration, it's very difficult to manufacture. So we typically use it in the closed loop gain fashion. In this lecture, we're not going to study about the open loop gain, so just ignore that for now. When we have the op-amp in a closed loop fashion like this with a feedback loop, there are two golden rules that we must remember. The first rule is V at this point and V at this point, V is the voltage, is always same. So V plus is equal to V minus. This is for an ideal op-amp. Since we have lots of V pluses going on here, so I'm going to change the symbol of this one and this one to say Vs as in power supply plus Vs minus. And now from here on, I'm going to call this terminal as V plus and this terminal as V minus. So golden rule 1 is V plus is always equal to V minus. So that's number 1. And golden rule 2 is the current flowing between these two is 0. Between V plus and V minus is 0. These are the two rules we must remember, and we'll use them when we learn about operational amplifiers and what all functions they are used for. All the examples that we are going to see in this lecture are an example of op-amps connected in closed loop fashion. So the first two common examples are of inverting and non-inverting. So to begin with, as we can see, this is the op-amp that we have studied. So yes, two terminals, inverting and non-inverting, V out, and there's a power supply. A lot of times we don't include power supply when we are drawing a schematic like this. So sometimes you will see op-amp with no power supply showing because it's implicit. For the inverting amplifier and non-inverting amplifier, the function is the same. It is to amplify the input. So for both of these cases, we know that V out is equal to some sort of gain. Let's just call it ACL, closed loop, times V in. Same thing here. V out is equal to gain ACL and V in. What we don't know is how much gain do we have from these op-amps. So we need to derive that. To begin with, we'll start with the inverting amplifier. So the inverting amplifier, it's called inverting because the input is going into the inverting terminal of the op-amp, whereas the non-inverting terminal is just attached to the ground. As opposed to non-inverting, here the input is supplied to the non-inverting terminal and the inverting terminal is just connected to the ground. So let's analyze the inverting amplifier so that we can exactly calculate how much gain we're going to have from this amplifier. We need to remember two rules. So the first rule is the voltage at this terminal and voltage at this terminal is always the same. So from here, from circuit analysis, we know that this terminal is connected to ground. Therefore, the voltage at this terminal is 0. And since the voltage at this point is equal to voltage at this point from the rules of ideal op-amp, we know that the voltage at this point is also 0 volt. So that we have utilized rule number 1. Then we know that the current is going to go from this direction all the way here. When the current flows through a resistor, there's going to be a voltage drop. So the voltage drop across R1 is V in minus 0 volt. That's the voltage drop across R1. So therefore, the current flowing through R1 is from Ohm's law, V equals IR. So the current is supposed to be V over R from Ohm's law. So we can say the current flowing through R1 is simply equal to I1 is equal to the voltage across that resistor, which is V in minus 0 volt divided by R1, or simply V in over R1. So that's what we know about here. Next, the second rule says that no current flows through here. So everything that's flowing here is going to go through this direction. Again, from Ohm's law, we know that I2 is going to be equal to, I2 is the current flowing through R2, is going to be whatever the voltage drop across R2 is divided by R2. Now what's the voltage drop across R2? It is 0 volt minus V out. 0 minus V out, or we can just say V out divided by R2. Since I1 is equal to I2, because there is no current flowing through here as we said, so everything that's flowing here simply just goes out from here. So I1 is equal to I2, thus we can equate these two. V in over R1 is equal to V out over R2. Our goal is to find what is V out over Vin, because that is the gain that we want to find out. So if I just made a simple mistake, sorry, I left out the minus here, so this is 0 minus V out, so this is minus V out. So if we rearrange, what we're going to see is V out over V in is equal to minus R2 over R1. So that's the result. That's the amount of gain we're going to have from inverting amplifier. So the gain is simply whatever resistor is connected here divided by whatever resistor is connected here. And the minus is we have an inverting amplifier. What that means is, so let's say you have an input voltage Vin supplied like this. The V out is simply the inverted version of this input but amplified. So if we were to draw the V out, it's going to look like this. So inverted and amplified, inverted and amplified. Now let's analyze non-inverting amplifier and see what kind of gain it gives us. For the case of non-inverting amplifier, also we want to know what is this closed loop gain. Let's analyze. So here we start with what we can with the rules that we have for the ideal op amp. So we know that the voltage here has to be equal to here. Now what is the voltage at this point? We don't know, because we'll have to analyze the circuit first in order to calculate what's the voltage at this point. So we don't know the value of that. However, we know that the Vin here does not have any resistor connected between this terminal and this input. Therefore, this V plus is simply equal to Vin. So the voltage at this point is Vin. And since the voltage of this and this must be equal according to the rule again, so the voltage at this point is also Vin. And you can see this point and this point essentially has the same voltage because there is no resistor. So this is Vin at this point as well. And what we are after is V out over Vin, some sort of gain. And we want to calculate this gain in terms of the elements that we have here, namely the resistors. So if you look at just this part of the circuit, this should look familiar from what we have learned in the previous lectures. So take a moment, you can pause. So this looks like a voltage divider, because voltage divider we know has two resistors connected like this, and then we have a voltage applied. So here same thing, you can say this is R1, this is R2, and here you have V, some sort of voltage, and then another side is ground. That is similar to saying you have a battery connected like this. So from the voltage divider, we know that the voltage drop across this R1 is R1 over R1 plus R2 times V out. So this is the voltage drop across R1. And voltage drop from this diagram here, you can see the voltage drop across R1 is Vn minus 0. So you can just say that the voltage drop is Vn, and from voltage divider analysis we know that this voltage drop is actually equal to R1 over R1 plus R2 times V out. Therefore, if we rearrange to get this right here, we see we are going to have V out over Vn is equal to R1 plus R2 over R1. You can rewrite this as 1 plus R2 over R1. So that's the gain that we get from a non-inverting amplifier. So again, if we want to understand what kind of output we will see from this amplifier, we will see similar to what we saw here, but non-inverting. So let's say the input V in is like this. The V out would be amplified by this much and will be in the same direction. So you have V out that is like this. So what we have learned from these two is, depending upon whether you want inverted output or non-inverted output, we can use one of these amplifiers, and you can easily control how much gain you want by changing the value of these resistors. So that's why it's easier to use op amps with the negative feedback. Next, we're going to learn about a few other use cases of op amps. So let's start with some of the mathematical operations such as integration, differentiation, and summation. The next thing we're going to learn about is the summing op amp. As the name suggests, it has something to do with addition. So let's analyze this circuit. So here we have three different input voltages. You can have more. So here just an example, we have three inputs and they're all connected to the same terminal. Here in this case to the inverting terminal of the op amp. So if you analyze this circuit, we're going to again start with what we know. And from the rules, we know that the voltage here is same as voltage here. Since this terminal is connected to ground, the voltage here is 0 volt. Thus, the voltage here has to be 0 volt as well. So that's what we know so far. So then, since these are voltages and this is 0, so there's a voltage difference, the current is going to flow here, here, here. So there is a current flowing here called I1, I2, I3. So if you were to calculate the current flowing through each resistor, we can use Ohm's law. Again, V equals IR, therefore I is equal to V over R. And for each of these resistors, we know that the voltage drop across this is V1 minus 0. And then if we divide that by the R at that, then that gives us the current flowing through R1. Similarly, the current flowing through R2 is voltage drop across R2 divided by R2, and similarly I3 is equal to voltage drop across R3 divided by R3. These are the currents, and then here they connect. We just have one node, so what the current coming out here at this point is summation of the current by KCL, Kirchhoff's current law from our previous lectures. So if this is I, then I is equal to I1 plus I2 plus I3, and we can just say that it's equal to V1 over R1 plus V2 over R2 plus V3 over R3. So that is the current. Now from the second rule for ideal op amp, we know that no current flows through the op amp. Therefore, all of this I that is coming here will flow through this resistor. And this resistor, I call it RF. F just stands for feedback resistor. So when the current flows from here to here, there's going to be a voltage drop across this RF resistor. Since the direction of current is from here to here, the voltage drop across RF is 0 minus V out. And then the current flowing through RF by Ohm's law is simply the voltage drop across RF divided by RF. So this is the current that is flowing through this from here. But we know, we have already said that no current flows through here. So whatever current is flowing from here to this point, the same current flows out. Therefore, this must equal that. So if I write it here, so V1 over R1 plus V2 over R2 plus V3 over R3, then V out is equal to minus RF V1 over R1 plus V2 over R2 plus V3 over R3. We can rewrite minus Rf over R1 times V1 plus Rf over R2 times V2 plus Rf over R3 times V3. So that is V out. So here the V out is the weighted sum of V1, V2 and V3. And the weights are Rf by R1, Rf by R2 and Rf by R3. Remember there is a negative here since we're feeding into the negative terminal. Now what happens if Rf is equal to R1, Rf is equal to R2, Rf is equal to R3? In other words, what if all the resistors are equal? So if all the resistors are equal, then these cancel and then you're simply left with V out is the summation of the input voltages, but you have a inverted because you're feeding into the inverting terminal. That's the summing op-amp. Next, let's look at the differential op-amp, where the output is the differential of the input. The circuit for the differential op-amp looks something like this. So here we'll need to introduce a capacitor, and we'll see why. We again do the circuit analysis. What we know is the voltage at this point is 0 volt, since this is just connected to the ground. Therefore, the voltage at this point is also 0 volt, and the voltage at this point is also 0 volt. So that's what we know from the rules about the ideal op-amp. Next, since this is voltage, some voltage, and this is 0, there's going to be current that flows through this capacitor. Now, the second rule of op-amp says no current flows through the op-amp. Therefore, whatever current flows through here, the same amount of current will flow through this resistor. If we call this current as ICI, you can, I just call this CI just to say that this is connected to the input end. And then this is the IFB, which is the feedback loop, so current flowing through here. These two are equal. Now what is the IC1 and what is IFB? You have to go back to the previous lectures that we have previously covered in this series in order to calculate what is ICI specifically. Well, I'll just mention it to you here again. For a capacitor, we know I is equal to C, which is CI dV dt. So whatever is the voltage drop across the capacitor, that is V here, and C. So this is what we know from understanding how capacitors behave. So this V is the voltage drop. So this is simply equal to V in minus 0. So I can say this is V in. Now this is equal to whatever the current is flowing through this resistor. The current flowing through resistor by Ohm's law is the voltage drop across this resistor divided by the resistor value. So the voltage drop is 0 volt minus V out divided by the value of this resistor, RF. Now things are simple. We're just going to rearrange few things in order to get what is V out. So CI dV dt, and this is minus V out, and I'm just going to take this RF here, and I can also take this V and this minus sign on this side just so we have a neat V out here, D dt. So this is the differential op-amp. So the output is the differential of the input, and we have this factor here determined by whatever the values of capacitor and resistor we choose. So you might ask what is the use case of this type of configuration. So the answer is, let's say you have an input that looks like a triangle. It's a triangular input, so this is input, but I want a square wave output here. So that's when you can use this type of op-amp, because if you do the differentiation of this triangular wave, you will get something that is square. Something like that. So that's a use case for the differential amplifier. Now, since we can do the differentiation, you might wonder that we should also be able to use op-amps to do integral operation, and you actually can. So let's take a look at the integral op-amp. For the integral op-amp, we also need to introduce a capacitor similar to how we had for the differentiator. So here I have two circuit diagrams. They're actually identical. I just drew them so that you understand that no matter how the circuit looks, we have to really start analyzing it step by step. So here, as you can see, this is something we are used to. So you have an input connected to the inverting terminal, and then this is grounded, and then you can analyze, because the current flows from here, and you analyze the circuit. So here, this is the exactly same circuit as that, but I've drawn it a little differently. So here, again, the input inverting terminal, the input is connected, same as here, and then the non-inverting is grounded, same as here. So they are exactly the same circuit, but I'm going to analyze this circuit just so we practice the circuit analysis skills as well. So here, from laws, or actually rules for ideal op-amp, we know that the voltage here is same as voltage here. So this is, since this is connected to ground, this is 0 volt. The voltage here is also 0 volt. That's what we know. Next, since no current flows through here, so whatever current is flowing here, the same current is flowing through the resistor. So this is 0 volt. So the current flows like this actually. So the current flowing through R1 is same as the current flowing through the capacitor CF. F is again for the feedback. So what is the current that flows through the capacitor? I equals C dV dt. So C dV dt, and V here is the voltage drop across the capacitor, which is V out. Minus 0, but I'm just going to skip that 0. And then about here, R1, the current flowing through here is the voltage drop across R1, which is 0 minus V in, 0 volt minus V in divided by R1. So if we rearrange this, ultimately what we want to know is what is V out and everything else. So that's what we want to know. So if we rearrange this, we are going to see, we get V in over R, and here dV dt, and I'm going to bring this CF to the other side, 1 over CF. In order to get rid of this differential, I can take integral on both sides with respect to time. So if I take the integral on both sides with respect to time, this side the differential and integral cancels and we have V out. Now on this side, we're going to solve this. So R and CF are constant, so I'll take those out of the integral R times CF integral of V in 0 t. So this is the output from an integral op-amp. So what's the use case of this op-amp when we arrange it in this fashion, where you have the output that is the integral of the input multiplied by some factor? So here this is used for waveform generation, and it's also used in the PID controller. You might not be familiar with the PID controller if you haven't taken a controller class, and that's okay. So just remember, we can do all sorts of these mathematical operations with the op amps. What we have learned so far, we have done inverting, non-inverting op amp, where you're just taking the output that is the amplified input. It could be inverting or non-inverting depending upon where the input is being supplied. And then we learned about the summing op amp, and then we learned about the differential and the integral op amp. There are a few other use cases of op amps, such as difference. So you can take the difference of the input, so you amplify the difference of the input, or you can use as a comparator. So we are going to study those in the next lecture. For this lecture, we're just going to stop here, and you can practice problems on this, find those on the internet, but if you want me to supply some problems, I can supply those as well. Just let me know in the comments. Thank you. Bye for now. I'll see you in the next one.